Here we're going to look at the current in a RL circuit. That's a circuit where we have a resistor and an inductor in series. And we're going to derive this familiar expression that gives you the rising exponential expression for the current as a function of time. So the important thing to realize is when this switch is closed, so when we initially have a circuit, the inductor is not going to allow current to pass. So initially it's going to resist and it will behave as an open circuit. And then the current will then increase with time. So we have current as a function of time. So if we want to find an expression for current as a function of time, let me label this as I, then the easiest way is probably to use Kirchhoff's voltage law. So we'd use KVL. So we would say that the EMF equals the drop in potential. Or we could say the EMF minus this potential equals zero. So that's your first step. Now this potential across the inductor is proportional to the inductance and to the rate of change of the current. So VL is L di by dt. So we replace that with that. We now have a differential equation where we have I and di. So we want to rearrange that to see if it's a separable differential equation where we can separate the variables. So how many variables do we have? We've got I and we've got t. So we want the t on one side and the I on the other. So the first thing you could do is to move your di by dt to the other side. So we have at least a little bit of separation. But now we need to multiply by dt to get dt on that side. We need to divide by L. And we need somehow to bring that I to the other side. So you'd need to divide. So I'm going to divide by V minus IR. So I'm going to divide by this expression here to get that in the denominator. I'm going to multiply both sides by dt, and I'm going to divide both sides by L. So now I have an expression where I have di and I on one side and dt on the other. And having that allows me then to address the differential equation by integrating both sides. So we put in an integration sign on both sides of this expression. So we're integrating here over time. So I'll integrate from t equals 0, that's the instant that the switch was closed, until some arbitrary instant t. And the current initially will be 0. The initial current will be 0 because it's an open circuit and there's no residual current in the inductor, and as I said, initially the inductor acts as an open circuit. And then I'll just put I here. So this is the easiest integral in the world because this is a constant. So you're integrating a constant with respect to time. So the integral is simply t. And this is a log, a natural logarithm, and then you multiply by negative, or you divide by negative r. So that's where that came from. And you then have the limits of the integration. And if you simplify that, so you put in I, and then you put in 0 and you subtract, we now have an expression with two logs, and remember, log A minus log B is equal to log a over b, so we can combine the two logarithms into one. Now, remember, what we're trying to do is to find I, so a little bit of manipulation is needed. So the first thing I'd want to do is maybe simplify this fraction. So it's Vs over Vs, which is 1, minus IR over Vs. Now, to get rid of the logs, because what we want is I equals, so to get rid of the logs, you would either apply the definition of log, which is e to the power that equals that, or just take exponential for both sides. So e to the power all of this is e to the power all of that, and the e cancels with the ln, leaving that. So we've almost arrived at our familiar expression. So remember, we're after I. So let's switch sides. Let's move this to that side and this to that side. And then you just multiply by VR over S, and you end up with this expression here. Now, if you remember that R over L is actually, L over R is actually our time constant, we can replace R over L with 1 over tau. So now we have an expression that's familiar. It has the time constant there, and you've got your EMF, and you've got your series resistance. So if we wanted to sketch this to see how it changes with time, so it's clearly a rising exponential. So when t is 0, you've got 1 minus e to the 0. 1 minus 1 is 0. So initially there's no current. We know that because it starts as an open circuit. And then as t increases towards infinity, the current will rise towards Vs over R. So if you were to replace infinity there, e to the minus a very big number would be almost 0. So 1 minus 0 is 1. So the current will approach Vs over R in the long term. What happens with the potential? The potential VL is the derivative of this, so it's the gradient. So the gradient is high, lower, lower, lower. Ultimately, it approaches 0. So your gradient would look something like this. And again, that makes sense. It says that at t equals 0, at 0 time, the potential VL is equal to Vs because there's no current. So at t equals 0, there's no current passing because this is acting as an open circuit. So the potential here is equal to the potential there, Vs. So that explains that shape there. So this is the gradient of that. So it's di by dt. So that's how we would derive this familiar expression. And it all started with Kirchhoff's voltage law, and then a little bit of manipulation. I hope you found that helpful.